Okay, this is video 4.1, soil mapping. So this is the final video lectures for module 1. And this video is going to go over maps and the mapping process. So soil mapping started in the 1960s. And it was kind of crude. You can see this was sort of hand-drawn, handwritten maps of polygons of different soil types. And over time, it got more precise where these polygons are ground truthed, and there's lots of data associated with these in a booklet. And today, then in sort of modern times, in the 2000s, we have modern mapping techniques using digitization. And we'll talk a little bit about all of these. Soil mapping in Alberta. So again, in the 1960s was considered the golden age of soil mapping in Alberta. There was standardized soil classification scheme, introduction of soil map units, and the Canadian Land Inventory was developed. There are around 40 soil survey reports throughout the province, and a soil survey report includes not only a map of polygons, but it also includes a booklet describing the parent material and the depositional environment and the fertility and the land capability of these sites. And so most of these 40 soil survey reports throughout the province are done in the agricultural zone or the white zone. Unfortunately, the last government-sponsored report was done in the early 1990s, and then the federal government disbanded the Canadian Land Inventory and stopped doing soil reporting. So all of the green zone, or the zone of forestry in Alberta, is not covered by these soil survey reports. However, they're still being mapped, and so why do we still map soil? So again, this is in the 1960s, with soil pedologists going out in helicopters to survey remote areas in the landscape, and we still have this in the 2010s. Here, these guys are soil pedologists who work for modern environmental consulting companies who are surveying soils for resource development. And so these are private sector pedologists. As I said, these are not working for the federal or provincial government. They're working for private consulting companies who work for resource extraction industrial partners such as forestry and oil and gas. And they do this for environmental assessment purposes. So these are for environmental impact assessments and pre-disturbance assessments for both forestry and oil and gas extraction. So basically these are baseline studies to determine land capability. And in the case of surface mining, the current requirement is that ecosystems be returned to an equivalent land capability function. So you need information before you surface mine an ecosystem. You need to know what that ecosystem was, what kind of soil was there, what kind of function it had, what kind of capability, what kind of productivity and fertility. So there's a lot of work going on in the green zone on soil mapping today. And soil mapping really begins with geomorphology and terrain analysis. So terrain and geology can be viewed as the base for all terrestrial disciplines. So the base for all terrestrial disciplines, including soils, veg, plant, and wildlife. Therefore, a clear understanding of terrain analysis is important for description of landscape features as well as soil characterization. Terrain classification includes both topographic form, which we've seen is very important for one of our soil forming factors, parent material interpretations, and geomorphic processes. So these are all important factors of soil forming processes that begin with terrain classification. What we can do is we can see how terrain influences soil patterns on the landscape. And so we've seen this before. I've taken this Chernozemic diagram and the solinetic diagram just for reference, and we can sort of imagine that this whole scale of this area is 1 to 3 kilometers. And what happens is we have a change in parent material here. So has increased sodium concentration for some reason. It looks like it's still till, but for some reason there's an increase in sodium concentration, making this a selenitic soil. And so again, if we look at topography, on the crest of the hill we have this rego, which is just an AH over C. Then we have a calcareous profile, which is AHBCA over CCA. This should be a CCA. And then we have our orthic profile. We have AH over BM over CCA. And then because we have a change in, and again, these are due to differences in moisture retention within the soil profile. And then here we get this drastic change in parent material for increased salinity. We start to have our selenitic soil. So it's still an AH horizon, but now it's on top of a BN horizon. And then when we have, again, we have a change to a more fine textured fluvial material with less sodium over here at the end of this. We go back to our orthic Chernozem with an AH BM CCA. And so in mapping these soils on the landscape, it's important to understand the way that topography is going to change the available moisture and soil profiles, and how that may change the expression of those soil forming factors and change the soil type. And so we can look at we can look at patterns on the landscape. And so all over the landscape, where we have different depositional patterns of parent material that may lead to different amounts of moisture in the soil, which may lead to different vegetations over time. Even though these sites are close to each other with similar climate, they may be very different expressions of soil. And so here there's a drastic depositional change here, where we have fine textured lacustrine material versus over here we have coarse textured alluvial material, or maybe it's glacial outwash. And what it does is it leads to some very different soils in this region. And so the brunissolic soils are on sand, on this coarse textured material, is represented by HT. And you can see here that if we were to try to draw a polygon on this, we have these little raised areas that are maybe different. Versus we have luvasolic soils on this lacustrine material, which is CCA, or CA rather, and we can sort of delineate that over here. And then we might have a mixture down in this depressed area of organic soils on peat, and that's down here in this sort of depressed area. We have these different HT and a mixture of brunissols and organic soils down here in this lower area. So this is basically soil mapping. What we do soil mapping is we have different tools, and some of these historic tools, so I'll just add that this is an historic tool that we don't really use anymore, but it's important to know what this is and how it works. Is we use air photos and an eyepiece to create 3D models. This is a stereoscope. The stereoscope is the eyepiece, and so you have two images. So you have 1 and 2 that are the same, but offset a little bit. And when you look through the eyepiece, the stereoscope, it creates a 3D image, and you draw lines with a grease pen or marker on photos or Mylar to sort of delineate polygons. You would look for topographic features, vegetation features to delineate polygons, and then you can measure the size of those polygons with a planimeter. And from there, from this first attempt at a map from aerial photos, you would go out and ground truth these. You would go out and you would dig soil pits to ground truth these and come up with data for your survey report. today we do it a little differently. We use GIS systems, and so these are used for both pre-field planning and post-field analysis. And basically what this is a digital mapping used to create polygons and statistics for interpretation. This is for interpretation. And so what you can see here is we can have different layers. We have a veg layer, we have a soils layer, maybe we have a fertility layer, and then we can have a water layer. And so what geographic information system, so GIS, is a very powerful software database. It's a spatially resolved database, and you can have all of this same information that these paper-bound soil surveys had are now digitized in this GIS software, and you can query the software. You can say where is the most fertile soil on clay texture, what area is that, and it'll point that out. And it uses vector and raster-based data. Other tools include 3D digital mapping. So this is a lot like what Google does. They drive around with these 3D cameras taking pictures of buildings, and then they put it into this spatially resolved map system for you to, and again, this is a type of GIS database where you can click on buildings. It'll tell you what commercial locations there are, what businesses there are there, where it is, and how to get there. So use additional software added to a GIS platform. These are just different examples of that digital software. Digital stereoscope models are built with overlap just like old stereoscopes, although now they require special hardware, computer screens, and 3D glasses to do this. But you've all used your phone, your smartphone, to navigate somewhere or to look something up in Google Earth, and that's where that information is coming from, this 3D digital mapping. Other tools for environmental surveying that can be used are LiDAR, which stands for light detection and ranging. It's a laser-based system that produces highly accurate digital elevation models, or DEMs for short. Laser swath scans the surface and measures the rate for return of the different signals. So it bounces off a certain wavelength and measures a change in the wavelength as it returns due to topographic features, captures all elements between the sensor and the Earth's surface, and can produce two forms of output, which are full Earth and bare Earth. And so these are examples over here. So this is it's aerial, so it's an airplane, a fixed wing plane flies with this laser, and it basically scans the Earth as it flies. The laser scans across a certain area, and it shoots light out, but then it also interprets the reflected light back. And what that allows you to do is produce a bare DEM, so a bare digital elevation model, as well as a full Earth model. And so of course the bare one is good for the topography, and the full Earth is good for doing analysis of vegetation. And so from here you would want to maybe try to start laying out your polygons. Here, just as an example, these polygons would be different. Obviously this looks like some kind of riverbed area, would be different than the alpine area. And then you might look for differences in vegetation. So this looks like different veg here that's associated with this little depression. So you would want to take some soil data from that specific location to determine if the soil is different from this polygon to this polygon.